Hello, Swen 656 students and professor. This is Curtis Sloan, and I will be giving a presentation on the design pattern that I chose, and that is the entity component system architectural pattern. And what I'll do in this presentation is I'll give an overview of the system and its benefits as well as its drawbacks. We'll quickly go over some UML of how it's typically implemented, my implementation. Then we will look at the code that I implemented using this pattern. And I'll try to be quick and intentional in this presentation because I didn't choose a very simple pattern. So there's a lot going on with it. But just for brevity, I'm going to get to it and try to be intentional and efficient with this presentation. So, the entity component system architectural pattern. All right. The great thing about the ECS is that it decouples the data from behavior and the identity that is associated with that data and behavior. This allows for more flexible and maintainable code. So the ECS pattern fundamentally embraces the principle of composition over inheritance. So that's actually the key reason for its flexibility and scalability. Now let's talk a few core concepts before we move on to the maintenance of this code. Now an entity is a unique object identifier that represents an object within a system. Now, it doesn't have any behavior and it doesn't have any data as well, but it acts as a reference for components. Now, a component is a container for the data. So it stores specific attributes, right? An example, if we were on needed to store an X and Y value, that would go in the component associated with the entity, and that would be associated with possibly a velocity system. So speaking of systems, a system contains the logic that operates on the entities with specific components. So systems, they iterate over all the entities that have required components, and then they apply the rules to those entities. Now let's get into maintenance. Maintenance is a very important subject for code that uses this pattern, right? So the ECS, it strictly separates the data, the behavior, and the identity. So this separation means that changes to one part don't require changes to the other parts. Now, this is a very modular approach that makes the code base maintainable. Now, since the entities are just identifiers and components, they're loosely coupled, so it's easy to add, remove, or change components without affecting the overall system. So that provides a high degree of flexibility to the software maintenance. Now, these pieces are very easy to reuse. So systems can be reused across different entities, and components can be combined in various ways to create new systems that provide new methods of behavior. So this reusability actually will reduce duplication of code and allow for easier updates and debugging. And finally, we have the ease of extensibility. So the ECS allows developers to extend the system by adding new components or new systems. So that way it can accept new data or behaviors without affecting existing ones already. So now let's talk about best practices with this complex architectural pattern. So it's very important to be granular with your components. So you have to design them to be small and focused, so this way they can be reused across different systems and entities. You should avoid making complex dependencies That's because reducing the complexity of the system will make it easier to maintain. Systems should be designed to fulfill specific processes and behaviors, and they should do this in bulk rather than one by one to improve the performance, and that supports an efficient system design. Now, the design should be data oriented. So if you focus on how the data flows through the system, the ECS aligns very well with that data oriented principle, and it allows you to emphasize structuring software to optimize data access patterns. And then finally, you should test systems individually. Since the systems are decoupled from the entities, you can test each system independently, and this would lead to much easier and more focused unit testing. So let's talk really quick about different scenarios. Right? I came across this pattern because I have a project, a personal project that I am building that it is a video game, and I discovered this pattern going through a book, and I just wanted to learn it. Now, it's primarily used in video games, but it's not just for video games. So, as an example, it could be used for simulation software, right? If you want to model an environment, you can model different, say, weather patterns or different elements, right? These would represent components of the weather, or an identity with an entity within the weather, right? So the component could include, wind data. It could include humidity. It could include other things like that. So let's say that the simulation would simulate different interactions between environmental factors. So you could create different systems to model those behaviors. Now, personally, my implementation of this is a really small video game, but we'll get into that as an example later on. First, we will go through the overall UML. So this is essentially what it would look like. You would have your entity. It would be filled with different components to capture data about the entity. And these components would be fed into systems for processing behavior. So if you want to look at a broader scope view, if I can very carefully zoom out here, right? This would be an example of having multiple entities. The top entity has its own components, the bottom entity has its own components, and each of those components is fed into a system to create different behaviors. So now we'll get into my example, my implementation, and what we will do is first go over the UML of my implementation. Let me very carefully zoom back in again. So again, as I said, we have, I did a video game example. It's a much more simple version of my project. I wouldn't say it is my personal project, but the ECS is the basis for essentially the game engine that I will be using. So first, we have the main game screen. I know you can't see it, but I'm doing air quotations around that. That's just a representation of what you would see in a camera. Now, in that main game screen, we have a manager that manages all the essentially the engine for the main game screen to interact with. Now, the main game screen is composed of just one manager, and the manager is composed of the system. In this case, this is the collision system, which is a implementation of the game system interface. game system just represents, it's the interface for all the behaviors. I would have called it system, but Java already has an object name system and it didn't very well like that. So now we have the entities, we have the concrete components, we have the abstract components, or the abstract classes of those components. So as you see, I am trying to get rid of a lot of code reuse. I'm trying to keep it simple. And then of course we have the component interface, which the control component and the movement component implement. And I have this as an abstract class that the graphics and physics component implement, or excuse me, extend. They are the children classes of the movement component. And I did that because they have they operate with very similar data, even though they have, that data has different purpose. So my reasoning behind this was, yes, they're very similar data, but since they have different purpose, it would have been a lot of code in these classes to work with, and I wanted to separate that because the physics component would have location data about different entities, and that could prove useful in other means. For example, if you need to track entities that aren't within your view, so that way your computer doesn't render them, but you're still tracking location and physics about them without having to without having to render them using the graphics data. So really quick, let's get into my implementation. I will do a quick demo and a code overview because I'm pushing 12 minutes. And again, just for brevity, I want to keep this as simple as possible. So this is my code. What I will start with is just a little demonstration, right? It's a spaceship with rocks, and it tracks collisions with the spaceship and the rocks. And of course, everything is, I don't know how to describe. Oh, he's stuck. I don't know how to describe when an object or an entity moves across one end of the screen, they come from the other. So it's a kind of a closed loop world. So that is my implementation, the final product of my implementation. I will go over the code really quick. As I said before, I put the entity component system within the engine, so it's very clearly broken out. And I will include the GitHub link to the discussion post, so that way if any of the other students want to review it or play with it, have fun with it. My only caveat is I use VS Code, so this would be my launch settings. Now, nevertheless, again, the component interface, it just uses one method. And then we have the control component, which directly implements the component interface. And then we have the movement component, which implements the interface. And here is some basic data about it. I've included the ability to pass the current position and the dimensions of the entity between these child classes of the movement component, simply because there's important data that both components need in order to operate effectively. Now, the graphics component extends the movement component. And again, I kept it very simple. We're still an abstract class here, right? Same with physics. It implements the movement component, but it is not as simple as the graphics component. And you see pushing about 130 lines of code with this class alone. So I found it very important to separate there. Now, right here, we have the player and the rock. These are the concrete classes of the components. We have the control component for the player, which just takes input from the keys and calls essentially changes the current data, right? I didn't want to do that in a system just because, again, you got to keep your systems very specific and very granular. Now, whenever you press the keys, the update method is called by the manager, which I will get to in a moment, and it passes the entity so that way it can operate. It can execute a specific method for rendering, and right here it essentially executes and changes data to be rendered on the screen. I won't get too deep into behavior simply because I didn't include a rendering behavior in this because the framework that I was using to render images and such, it's all abstracted away by the Ligdx framework. Let's get into the implementation of the graphics component for the player. It just grabs the texture, generates the sprite so you can see it, and then again on the update, that is called by the manager. And then the physics, the player physics component, again, keeping it simple. And big thing is it's called by the manager. And of course, we have some methods that are inherited from the physics component that is executed. So it's essentially the same for the rock. In fact, I don't even have any use for the control component of the rock because it just is generated and it kind of does its thing. The rock graphics component is very similar to the player component. It's just it has a different image for texture. Now the physics, it's immediately generated and executed on. This way it has no control, right? So these components are used by the manager so that way they can be registered to a system and also be updated. I do have some other methods in here, for example, get random. That is more for generating random numbers. I do need to go over the entity. So we have bounds, and this is just more for gameplay, getting the positions to pass to wherever they need to go, that data needs to go. Essentially, it's mainly getters and setters. The big thing I want to talk about is the register components method, and that registers the component to the collision system. So that now we're getting into the systems, and I'll go over that in a minute. We are registering these components to the collision system because those are the components it requires to create the behavior. Moving up, we have the update current entities that aggregates all the current data for physics and graphics to be displayed on the main game screen. Now, one thing that I included in this was the singleton pattern, because the game only needs one manager, and same with the collision system, it only needs one collision system, right? So going back to the type of pattern that this design pattern is, it is an architectural pattern, and I actually used a composition of multiple patterns in order to get the behavior I wanted, because Java has its own unique idiosyncrasies that would cause a different implementation for Java of the ECS pattern than, say, C++. And that's something I'll get into a bit, right? Moving on, we're going to look at the entities. Again, well, I'll talk about the pattern in a moment. Entity is very simple. We have the components that are associated with it. We instantiate the concrete implementations of the abstract classes. So control component, physics component, graphics component. These are all the abstract classes, but using polymorphism, when I create the entity later, I get specific about the component that I want. And these methods associated with it, for example, these two, they're associated mainly with the framework I'm using for rendering to the screen. This is for a component control, all right? There's I created this specific method so that way both of the physics and the graphics component can be operated on, the data can be used at the same time. And then I snuck another different design pattern in there. I used an entity factory to create all my different kinds of entities, which again I will get to in a moment. Go to screens here. So I did instantiate the player and the rocks from the main game screen, just because that screen would require those entities. However, I did immediately associate them with the manager instance, so that way they can all be managed by the manager, and the behaviors can be derived through the manager, right? These are methods that are required right here from the Ligdx framework. The body of the implementation is right here in the show method. This just primes everything for the game, right? So I'm setting the player, I'm setting the rocks, I'm setting dimensions, bounds, player position, rocks position, and then of course registering the components with the system. So now we can get to the system. Going to the game system interface, I have two main methods here. Is to register the component and remove component. Now this is a bit reminiscent of the observer pattern. However, I think it's a bit more like I would say it's more of a reverse observer pattern, because it is the observer pattern with the subject that registers the observable, or the observers rather. The observers take data from those components, and the observer would take data from the subject and do whatever it would with that. And this is a bit reverse. I'm registering what you would think would be the observer with the game system, so that way the game system can operate on the data coming from the observer, right? So coming from the component in this case. That's why I said it's a bit like a reverse observer pattern. So again, I'm using a singleton for the collision system, because there only needs to be one collision system for the game. And we're getting to the components that are going to be registered with it. I don't have them all aggregated into a single list simply because the player physics component is going to be segregated from the rock's physics component. Now, just as you would expect, register components, take a component, check the instance of, put it where it needs to go. Now, the main behavior for this system is that it checks for collisions. So it checks to see if a rock has overlapped with the player, and then from there it is meant to just bounce the player off the rock, right? That is the behavior of this system. You could do a lot of things with the ECS for video games. For example, as I mentioned before, if there's let's say you're playing a multiplayer game and there are 20, 30 players in total in the game with you, but you can't see all 20 and 30, the game needs to be able to track where those other ones are, so that way if they come within your field of view, you would be able to render them. Now, with that done, let's take just one little moment to get away from all the theory, to get away from all this, this complex pattern stuff, and put our mind at ease with a very simple game that is mildly entertaining at best. Just kidding. Let's get into the benefits and the drawbacks. So, one of the most obvious benefits of this architectural pattern is that there is a very clear separation of concerns. There's separation between the data or the components and the behavior of those components, as well as the identity associated with the data. Right? Everything is very clear and separated, yet it's composed well enough to where it works. There is a very big flexibility and extensibility to this pattern, and that's because you can create new components or systems pretty much not at runtime, but on the fly, right? Let's say you wanted to add a location system, or you wanted that starship to be able to shoot a laser, right? That laser would be an entity that could also take the three main components, the control, the physics, and the graphics, so on and so forth. So it's very quick and easy to add new things onto it and test different ideas. Now, the big thing I want to talk about is performance, and that's because it is, this pattern has been optimized for performance, particularly in systems where the entities share the same components. So that way, data is actually able to be processed in bulk. Right? Going back to those simulations, you can optimize memory layout, and it's actually very common that this happens because as I was researching and learning more about this entity, the ECS pattern, a lot of the implementations were in C++, simply because you have more control over the memory, right? You can have those contiguous memory layouts, so you could increase performance, right? And actually, most of the videos where that I found, or videos and material rather, it was a big consensus that Java was not a very good language for this. I tend to disagree, just because the data structures in Java are a bit they're more safe. Anyways, let's get to the drawbacks, because I'm pushing 30 minutes. So in conclusion, the drawbacks. This is very complex. it took me a while to learn this, figure it out, and implement it. And I was kind of already in the way of implementing it, and it was an architectural pattern, so it just kind of fell in my lap and worked out that I was doing a project that I could do a academic project on this, right? There's a big learning curve. Like I said, I was doing this for maybe 2 weeks before I knew about this project, so I was already in the process of learning it. Going back to the topic of the memory, you could very quickly shoot yourself in the foot with the memory piece, especially if you're using a language like C, because managing memory requires using pointers and allocating heap memory and all that fun stuff, and that can be a very complex subject if not carefully managed, because you can shoot yourself in the foot, you can cause crashes and all that fun stuff. So now if you made it to the end, I thank you very much. You are a trooper. I hope this was informal or informational to everybody who made it all 31 minutes and 4 seconds of the video so far. I had a great time learning about this. I had a great time implementing this design pattern, and I even got to be sneaky and throw in some other patterns as well. Thank you so much.